The number of male and female customers entering a cafe in a randomly chosen 15-minute period have independent Poisson distributions with means 1 and 2 respectively. Find the probability that in a randomly chosen 30-minute period there are more than 5 customers entering the cafe. So we let x and y, let x, y be the number of male and female customers entering in 30 minutes, respectively. Then I can say that x, in 15 minutes I'd expect 1 man, so in 30 minutes I'll expect 2. And similarly for y, the number of females, in 15 minutes I expect 2, so in 30 minutes I'll expect 4. And I'm asked for the total number. I'm asked to find the probability that there are more than 5, so I don't care about gender, so I can add them together. So the x plus y follows a Poisson 6. So this is asking me to find the probability that x plus y is, there are more than 5, so is greater than or equal to 5. So to do this, I can, wait, more than 5, right? More than 5 means it cannot be equal to, sorry. So this is the probability that it is strictly bigger than 5. That's of course 1 minus the probability that x plus y is less than or equal to 5. And I do this because my Poisson CDF on my calculator, it has to have this less than or equal to sign. It can't work on a bigger than or on a less than or on a bigger than equal to. It needs to have less than equal to. So I go to my trusty GC, still from a previous question, so let's clear all this stuff. I go to my distributions. I look up my Poisson CDF. Now my value for lambda, my mean, was 6 for this period. My x value is 5. So what's the probability it's less than or equal to 5? That comes out to be 0.44567. Now I'm not interested in that number per se. I'm interested in 1 minus that number. So this is 0.55432. So my answer here is equal to 0.55432, which is approximately 0.55423 SF. Fantastic. Part 2. The cafe is open for business 6 days each week. Using a suitable approximation, find the probability that in a period of 10 weeks there are no less than 30 days on which there are more than 5 customers entered the cafe between 9 a.m. and 9:30 a.m. Wow, okay, that's a bit of a headache. Let's break it down a little bit first. So let W be the number of days on which more than 5 customers entered between 9 and 9:30 out of 60 days. So what can you tell me about W? Well, W is counting the number of successes, if you will, out of 60. So it fits rather nicely into a binomial distribution. And what's the probability of having more than 5 customers entering? Well, that's what I just found out from my previous part, 0.55432. Right? Now, because n is large and np is bigger than 5 and nq is bigger than 5, so since n equals to 60 bigger than or equal to 50 is large, and np, which is equal to 33.25, is bigger than 5, and nq, which is equal to 26.74, is also bigger than 5. Therefore, I can use the normal approximation to the binomial distribution. So W is approximately binomially distributed with mean of n times p. so 33.2592, and a variance of n times p times q, so that comes out to be 14.8229, and this is an approximation, so only approximately. So we're asked to find the probability that the number of days on which more than 5 people enter in this 10-week period uses to find the probability that in a period of 10 weeks there are no less than 30 days. No less than 30 days. So we want to find the probability that W is no less than 30. In other words, W is greater than or equal to 30, but I'm using a normal approximation, so I need to do my continuity correction. So my continuity correction is 29.5. Why? Because I want to include 30, and I'm going to larger values. So to make sure I include in 30, I'd take all numbers bigger than or equal to 29.5 by my continuity correction. So again, you can key this into your GC. I'm not going to do it this time, but it comes out to be 0.83623 SF. Okay, what about part 3? So part 3, in a particular 15-minute period, there are less than 5 customers entering the cafe. Find the probability that at most 2 male customers entered the cafe during this 15-minute period. Okay, so for this 15-minute period, I'm going to let A and B be the number of men and women entering in the 15-minute period. So I know that A is Poisson 1. It basically told me that right at the start. B is Poisson, what am I doing? B is Poisson 2, and that A plus B shall be Poisson 3. Happy days. So what am I asked to find? I'm actually asked to find the probability that no more than 2 men entered, given that fewer than 5 people entered. So, what's this? Well, this is the probability that A is less than or equal to 2 and A plus B is less than or equal to 4, divided by the probability that A plus B less than or equal to 4 is less than or equal to 4. So this one on the bottom line is not too bad to calculate. I can do that very easily using my Poisson CDF. What about this one on the top line? Well, I need to unfortunately split it into cases. So what are the 3 possible values of A I could take? I could take A is 0, A is 1, or A is 2. And when that happens, what happens to B? So if I take the probability that A is equal to, not less than or equal to, A equals to 0, then what can I say about B? That means that B has to be less than or equal to 4. Oh, and I can multiply these together because A and B should always be independent from one another, but A and A plus B, obviously they are not independent from one another. So I need to split it up into an A and a B on either side of the and sign. So in this case it's A is equal to 0 and B is less than or equal to 4, or this is a mutually exclusive case where A equals to 1, in which case B is less than or equal to 3, or, again mutually exclusive, A equals to 2, in which case B must be less than or equal to 2 as well. And all of this should be divided by the probability that A plus B is less than or equal to 4. So again, you can go and key all of these into your GC. There's no problem there. Again, I'll leave that fun part to you. This comes out to be 0.96723 SF. So part 4, last question. Explain why the Poisson distribution may not be a good model for the number of people entering the cafe. So you think about a cafe, you think about the fluctuations during the day. This is very bad for the Poisson distribution. So you can say the rate at which customers enter the cafe may vary or fluctuate wildly, e.g. more at lunch, more during lunch, fewer. Let's be a little bit facetious. Did they say what time this cafe is open? No, so maybe fewer after dark, or fewer after dinner, or something like that. So the key idea, though, is that the rate at which people enter this cafe is not going to be constant. It's going to vary, of course, as the day goes on. So that means that it's not a good distribution, not a good situation to be modeled with the Poisson distribution, which requires us to have a fairly even distribution of events over the course or over an interval.